This lesson is going to introduce us to the concept of electric potential. Now remember, electric potential is going to be different from electric potential energy. First off, we're going to start from at defining it and then how we calculate it. Then we're going to go into some pictures and work associated with equipotential lines. Okay, first off, when we analyze electric force, we looked at the force between two charges, Q1 and Q2, and that was Coulomb's law. Okay, and then when we looked at the electric field, we only looked at the field or the relative force on a from one charge. Okay, so electric field looks at one charge, whereas electric force looked at two of them. Okay, similar concepts exist for the electric potential energy. When we have electric potential energy, we looked at the stored energy associated with two charges that I've held in position. They're either going to fly apart if they're repulsive or attract together if they're not. Okay. However, I can do the same thing that I did for electric field, and I'm going to look at the electric potential, or the potential energy that would be associated if I put a positive test charge somewhere out there. Okay, so electric potential is going to be the electric potential, or another term we'll use for it is voltage, associated with a single charge. Every point in space will have a different potential associated with it. Okay. So like I said, electric potential and voltage are going to be synonymous the way we're going to be using it. Okay. I may also use the term voltage differential, or delta V. This requires that I actually have two different points and the difference in voltage between those 2 points. Okay, the units for electric potential is going to be volts, or joules per coulomb is another term for it. Okay, so when I have a point charge, okay, the voltage or the electric potential at a distance from that charge is going to be given by Q over R. Okay, it's that same K, 9 times 10 to the 9th. Q is the central charge, and R is how far I am from the center of that charge. Okay, electric potential is a scalar, so the sign of the charge is going to be important. It is quite easy to have a negative voltage. Okay, negative 100 volts is perfectly fine. Okay, by definition, when the distance is so far away, okay, again, just like I did for electric field, okay, when I'm so far away, R becomes infinity, and my voltage basically becomes 0. Okay, so remember, at infinity, my electric potential will be 0. Okay. Because at every single, there will be multiple points that have the same electric potential, I can connect all those points and create what we call equipotential lines. Okay, equipotential lines for a point charge, remember, KQ over R. K and Q don't change, so only R changes. So everywhere that's at the same distance will have the same electric potential. Okay, so in this picture that we have, okay, that looks like, I don't know, a target or something like that. I have these concentric rings, and these rings are at the same potential. So V1, everywhere on V1 has the same potential. V2, everywhere on that red circle has the same potential. V1 and V2 are different, okay? But those lines are the same. And that's what we call equipotential lines, okay? And they basically approach 0 as I move farther away. For a positive charge, they're large numbers close to the charge, like 500 volts, and then they approach 0 as I go farther away. Okay, for a negative charge, it would be like minus 500 close to the charge and approaches 0 as I go farther away. Okay, for those of you who are hikers, okay, equipotential lines are similar to topographical maps. Remember, the concept of voltage and altitude are similar, okay, except voltage is for electric fields and altitude is for gravitational fields. And but the concepts are similar, okay? Higher voltage implies more potential energy if I put a charge there. Higher altitude implies greater gravitational potential energy if I put a mass there. Okay, so we will also need to be able to draw the electric field and given equipotential lines, or draw equipotential lines if I have a field. Okay, so there are 2 rules that we must follow. Okay, the first rule if I have equipotential lines, is that the electric field must always be drawn perpendicular to the electric field. So for instance, okay, my electric field here at the x would kind of point slightly up and to the right, because it needs to be tangent, or not tangent, it needs to be perpendicular to my equipotential line. Similarly, over here, it would also be perpendicular. Okay, if I have an electric field, by definition again, the equipotential lines would be perpendicular everywhere that they cross. Okay, so that's the first rule. Okay, you always draw the equipotential lines and electric field lines perpendicular. The second rule is, because electric field is a vector, it has to have a direction. Okay, it has to have an arrowhead, and the electric field basically always goes in the direction of decreasing voltage. It basically always points downhill, electrically speaking. So find the smaller and smaller numbers. Okay, in this case, the smaller numbers are to the right, or the lines to the right. So these arrows would point to the right. Okay, they basically point downhill, electrically speaking. Okay. When I have a uniform electric field, okay, remember, two parallel plates, okay, I have a positive plate here and a negative plate. These are parallel plates, and they are basically there to generate what we call a uniform electric field. Uniform basically means same direction and same magnitude. And this is going to be true everywhere in the region between the plates. So this entire region has the same magnitude and direction associated with the electric field. Okay, or in other words, okay, this point has the same electric field as this point, as this point, as this point. Okay, they're all the same. And as a result of that, okay, my equipotential lines are going to be horizontal, because that's what's perpendicular. And we have a formula that says the different change in voltage is going to be the magnitude of my electric field everywhere times the distance. Okay, so what it means is that my voltage will change linearly with distance. So if this is 0 and 100 volts, okay, and my spacing is 10 centimeters, okay, every 2.5 centimeters would correspond to a 25 volt increase. Okay, and the other thing about equipotential lines is the spacing voltage wise must be the same. Okay, so in this case, 0 to 25, 25 to 50, 50 to 75. That's an arithmetic series. It increases by the same amount each time. Okay, however, when I have a point charge, okay, the electric field is not uniform. So my spacing here is not going to be uniform. Okay, if I had a third line, it would be much farther away. Okay, the distance between V1 and V2 in terms of meters is going to be less than the distance between V2 and V3. Okay, so because I have that uniform electric field, I have this new formula that says the difference in voltage is going to be linear with distance, and I can calculate my electric field given that. So what happens when I have multiple charges, and how do I calculate the potential given that? Okay, electric potential and the net electric potential at a given point is the sum of all those voltages from the individual charges. Okay, paying attention to the minus signs generated from minus charges. And there is no direction here because electric potential is a scalar. So it really doesn't matter that I'm at 45 degrees or 27 degrees or 130 degrees. The only thing that matters is the distance. So here's a sample problem where I have a positive charge Q1 at 5 millicoulombs at minus 8 meters, and then a negative charge of minus 2.5 millicoulombs at x equals positive 3 meters. So I wanted to find the net electric potential at x equals minus 2, right there. Okay, so I basically calculate the voltage from each one of the charges, paying attention to the distance. Okay, so 8 to minus 2 is a difference of 6 meters, and 3 to minus 2 is a difference of 5 meters. And just plug my charges in and do the math, and I find that my net potential there is just going to be 3 times 10 to the 6 volts. Okay, and what that's really going to help me to do then is calculate work. Okay, because voltage gives us a shortcut to calculating work. Instead of calculating potential energy every single time, and remember, to calculate potential energy, I pretty much need to have 2 point charges. I don't always have 2 point charges because sometimes I don't know what's generating the electric field and the electric voltage. Or maybe it's a plate. Okay, so instead what I can do is I can use those voltages and calculate work by applying a formula that says the charge that I'm going to be bringing in, the moving charge, or that's why I use the lowercase q here, okay, the moving charge times the change in voltage as this charge moves. Okay, that represents work, or the change in kinetic energy for this moving charge. Okay, so as this charge moves from voltage A to voltage B, okay, it experiences a change in its kinetic energy because of the force generated from the field. Okay, and so I'm going to be able to calculate kinetic energies, and if I have masses, I can calculate velocities, all by seeing what voltage did I start from and what voltage did I end at, and then multiplying it by Q, the sign of my charge. Okay, and that's how we're going to be using equipotential lines, and we're going to do a bunch of problems associated with that. Okay, thank you.